Hi, I'm Ananta Raguraman, a student of Purdue University in the ECE department. Today I'm going to talk about maximum likelihood estimation. It is a lecture done by me. To learn more about lectures, please visit www.projectria.org. The overview of today's talk is going to be: first, I'll start with the review of Bayes' theorem. I'll follow it up with a discussion about the Bernoulli distribution, and then I'll introduce the topic of maximum likelihood estimation, and I'll tell you how you can apply maximum likelihood estimation in case of a Bernoulli distribution. We'll then proceed to a Gaussian distribution, and then we'll talk about how MLE can be applied to estimate parameters of the Gaussian distribution. And then finally, we'll look at when MLE would work and when MLE might not work. Okay, let us begin by reviewing Bayes' theorem. Let us consider an example of tossing a die. So when you throw a die, you might get any one of the following results. You can get a 1, 2, 3, 4, 5 or 6. So let us think of an event where we want to know whether after throwing a die we obtained 2 or not. Let us call this event 1, and let us call an event 2 as the event that when I throw a die, I want to know whether I get an even number or not. So E1 would be represented by a random variable x1, which would be 1 if I get 2, and it would be 0 otherwise. Similarly, E2 would be a random variable that's defined by x2, which would be 1 if I get an even number, and it would be 0 if I get odd number. So let me assume that I've thrown the die twice. So if I want to calculate the probability with which I get 2 on the first throw, which means I get x1 equals 1, and I get an even number on the second throw, x2 equals 1. So let me also denote that this happened first by adding another number here. So this would be the first throw and this would be the second throw. So by Bayes' theorem, what we actually can calculate is joint probabilities like this. So a probability like this, where you want to calculate the probability with which 2 events would occur, would be given as probability that x11 would be 1 multiplied by the probability that x22 would be 1, given that x11 is 1. So you can think of it intuitively as assuming that this happened first, and then you want to calculate the probability that x22 would be 1, given that x11 already happened. So this together would give you the joint probability. As you can see, this is also equal to probability that x22 is 1 multiplied by the probability that x11 would be 1, given that x22 equals 1. So finally, one last property that we'd like to know is this. when you have two events, E1 and E2, if these two events are independent, then you have probability of E1 given E2 equals probability of E1. Similarly, probability of E2 given E1 would be probability of E2. This is because the knowledge of whether E2 happened or not will not affect the probability with which E1 would happen. That is because E1 and E2 are independent. We will use this later in a slightly modified form. So now that we have recollected Bayes' theorem, let us talk about a Bernoulli experiment. So let us talk about a coin toss. So let me assume that I have a coin, and let me define a random variable x, which would be a result of a single toss of a coin. My random variable x would take the value 1 if I get a head, and a value 0 if I get a tail. A Bernoulli distribution is a probability distribution that defines the probability distribution of x. As you can see, it's a discrete probability distribution, and it can be represented like this. When we look at this, it might seem very complicated, but in practice, in reality, it is not. So what I've actually done here is I've actually made an assumption. So the assumption that I've made is that the probability with which x would be 1 is mu. So I've assumed that the probability with which a coin toss would result in a head is a number mu, and this would automatically mean that probability of x being 0 is 1 minus mu. So if you look at this, you can see that x can either take the value 0 or 1. So probability that x equals 1 given mu is mu to the power 1 multiplied by 1 minus mu power 1 minus 1, and you can see that this is equal to mu. Similarly, probability that x equals 0 given mu equals mu to the 0 multiplied by 1 minus mu power 1 minus 0, which is 1 minus mu, which is what we have seen earlier. So this is a parametric representation of the probability distribution for a Bernoulli trial. Now that we know what Bernoulli distribution is, let me introduce the topic of a likelihood. So let us assume that I have tossed the coin n times and I have obtained the outcomes x1, x2 up to xn. You may recall that any of the xi's where I equals 1, 2 up to n is either 0 or 1, where 1 represents an outcome of head and 0 represents an outcome of tails. And like earlier, we'll assume that probability of x given mu would be mu to the x multiplied by 1 minus mu to the 1 minus x. So I'm going to introduce another concept. We are going to assume that all the xi's are independent and identically distributed. We denote this by the short term IID. So what independent and identically distributed means is that when I say independent, it means that the outcome of xi is independent of the outcome xj for any I and j from 1 until n when I is not equal to j. This is the independence probability, and the identically distributed means that all of the xi's were sampled from the same Bernoulli distribution. Note that to do a maximum likelihood estimation, you do not require the samples to be IID. The advantage is that IID simplifies the computations a lot. So that is the only reason why we use IID. So let us denote D as a set of outcomes that we already have. Now the likelihood function is nothing but the probability that we have obtained D given that we know what mu would be. Or in other words, this is the probability of getting the outcomes x1, x2 up to xn given that we have sampled from the Bernoulli distribution with parameter mu. So since x1, x2 until xn are independent, this probability is equal to probability of x1 given mu multiplied by probability of x2 given mu, and so on. Now we have likelihood function as product of and as we already know, probability of x given mu was mu to the x multiplied by 1 minus mu to the 1 minus x. So substituting this formulae into our equation 1, we get so this is the likelihood function for the Bernoulli experiment that we have done so far. So from this you might have guessed what maximum likelihood estimation is going to be. So the way we are going to use maximum likelihood estimation is that we have already obtained the results D, and using D we are going to get the best estimate, which as of now is going to be called as the MLE estimate for us because this is the method that we know the best now. Estimate of mu. I told you initially that x is distributed depending on the parameter mu, but we have never gotten a single value of mu. I told you that this is the distribution of x given a parameter mu. So what we are trying to do now is that since we have all of this data, from this data we are trying to get a particular value of mu, which would probably make getting this particular set of data the most likely. So what we want to do is maximize the probability of getting D given mu. So we are going to maximize L of x, and we are going to choose the value of mu that would result in maximum likelihood. As you can see, since L of x is a likelihood function, without going into too much details, you can see that the value of mu that maximizes L of x will also be the value of mu that maximizes logarithm of L of x. So the advantage of working with logarithms is, here you can see that L of x is a product of many parts. So when you actually take logarithm of L of x, you end up with sum of lot of parts. We are going to see how it is going to work now. So I am going to take logarithm of the likelihood function and I am going to maximize it. So this is why it is called the maximum likelihood estimation. Note that the product that we had earlier now has become a sum. This is what we have ended up with, and as we know, this is going to be equal to now how do we maximize the log likelihood function? So this is called the log likelihood function. So one way to maximize it is to take the derivative of the log likelihood with respect to the parameter that we want to choose and then setting it to 0. So we are going to do that now. So we are going to do differentiation of log of likelihood function over the parameter, and we are going to set it to 0. So we can see from here that it is going to be, the xi is going to stay as it is. I'm going to get a 1 over mu here, and this is going to stay as it is, and I'm going to get a 1 over 1 minus mu here, and then I'm going to set it to 0. I'm sorry, there is a correction. When you differentiate log of 1 minus mu, we don't just get 1 over 1 minus mu, but we also have to differentiate this and we'll get a negative 1. So this is going to be negative 1 times this factor. So instead of this, we're going to have a negative sign here. So continuing with the derivation, after we equate the differential of the log of likelihood to 0, we are going to get xi times 1 minus mu minus, I have just distributed the summation to the two terms, and you know that this 1 minus mu and nu don't interfere with the summation, so we can take them outside. So I'm going to get 1 minus mu times sigma xi minus mu times sigma 1 minus xi, and this is equal to 0. So let us call sigma xi as p. If you recall, you would know that xi would be 1 if I obtained head on ith trial, or it would be 0 if I obtained tail on the ith trial. So sigma xi is nothing but the total number of heads that you have obtained from trial 1 until trial n, and sigma 1 minus xi would be the total number of tails that we obtained in the n trials. So let us call it by n minus p. So the summation becomes 1 minus mu times p minus mu times n minus p equals 0. Simplifying this further, we get mu equals p over n. For the random variable x, which is 1 when we get a head and 0 when we get a tail, is the total number of heads that we have obtained in the n trials over the n trials. It seems very intuitively correct. Just remember this result. We'll be looking at it later on, but this is the flavor of MLE. So in MLE, we use the data that we have already seen to estimate the parameters of the distribution from which we have sampled our variables. Now let us look at one more example, which is the Gaussian distribution. So I'm going to focus on one-dimensional Gaussian, but you can extend the results that we are going to see here to multi-dimensional Gaussians. The essence of MLE remains the same. As you might see after this example, that the way you apply MLE more or less remains the same, just that the distributions that we are drawing our samples from are different each time. So earlier we saw a Bernoulli trial, which is a discrete probability distribution, and now we are going to look at a continuous probability distribution, which is probability of x. We are going to have two parameters here, a mean and a variance sigma square. Remember that the mean that we are going to denote here is different from what we saw earlier on for the other distribution. And the mathematical expression that relates x with mu is so this is the parametric form of Gaussian distribution. Very crudely, a Gaussian distribution looks like this, where this is the mean and your sigma square would be approximately distributed like this. And your Gaussian distribution, as you can see, extends over the entire real axis. And for every single point on the x-axis, you can find the probability density. This is point xi. You can find out the probability density. Now again, let us assume that we have a sample set D of samples that you have already obtained from the Gaussian distribution. and let us denote it by x1 until xn. So we have n samples that we have already sampled from the Gaussian distribution, and our goal is to estimate the parameters mu and sigma squared. So like how we estimated the parameter mu in a Bernoulli distribution earlier on, now we are going to get a maximum likelihood estimation of mu and sigma square. So the first step in maximum likelihood estimation would be to write the likelihood function. So the likelihood function here is going to be, again, is going to be probability of getting D given mu and sigma squared. And this is going to be probability that we have obtained x1 until xn given mu and sigma squared. And we are going to assume that x1 until xn belong to IID. So what this would mean is that this would become a product of probability of xi given mu sigma squared. Like before, we are going to take the log of the likelihood function and we are going to convert the product into a summation. And we are going to equate the log of this function to 0, right? We want to, sorry, not the log of this function, but the derivative of the log of this function to 0. So once we have the log likelihood, we are going to do the derivative of log likelihood over the parameters, and we are going to set it to 0. So as you, if you want to recall, probability of xi given mu sigma squared is given as 1 by root 2 pi sigma multiplied by an exponential function like this, x minus mu the whole squared over sigma squared. It is going to be xi minus mu the whole squared minus n over 2 log sigma squared minus n over 2 log of 2 pi. So you can see that if you take the logarithm of this function, you would end up with this for the summation. So now that we have this, as you know, we are going to take the derivative of the log likelihood and set it to 0. So first I'm going to differentiate with respect to mu and then find out mu ml. So when I differentiate this expression with respect to mu, I know that these two are going to go to 0 because they are not dependent on mu. So I'm going to get 2 times I equals 1 to n xi minus mu equals 0. So this simplifies to n mu equals sigma I equals 1 to n xi, or my mu ml is nothing but the average of all the xi's that I've obtained so far. Again, this seems intuitively very correct. So if I want to find out the mean of a distribution from which I have sampled a lot of samples, Then I just take all the samples that I have and calculate the mean of those samples. What about the variance? So to just recall, we had the log likelihood function as so I'm now going to differentiate this with respect to sigma squared. I'll know that this term will go to 0 because it will not depend on sigma squared. And now, instead of having mu here, since I already know what mu ml is, I'm going to take this as mu ml. So this is going to be negative 1 over 2, and I have a sigma squared here. So I'm going to get sigma squared to the minus 2 into sigma I equals 1 to n xi minus mu ml the whole squared. And since I differentiated with respect to sigma squared, this negative sign is going to become a positive sign, and this term would become 1 over sigma squared, and I'm going to equate it to 0. So I'm going to cancel 1 sigma squared, and I'm going to get 1 over 2 sigma squared times this expression equals n over 2. Again, I'm going to cancel the 2 and take the sigma squared here. So I'm going to get sigma squared ml equals 1 over n, sigma I equals 1 to n xi minus mu ml the whole squared. So this is the maximum likelihood estimate of my variance from the data that I have already obtained. So as you can see, you can apply this technique to many distributions. So you need not even have the assumption of IID, just that it simplifies the mathematical expressions that we obtain. So now that we have seen the maximum likelihood estimation technique for a Gaussian distribution and a Bernoulli distribution, let us just take a step back and then see, does it always work? So I asked you to keep the mu maximum likelihood estimation that we did for the Bernoulli distribution in your mind. To just recall, for a Bernoulli distribution that we saw earlier, the mu ml was obtained as p over n. So let us assume that we had a data where we got 1, 1 and 0. This would mean that I got a head in the first attempt, head in the second attempt, and tail in the third attempt. So my mu ml for the fourth attempt, if I want to estimate the mu with which I'm going to get a head, it is going to be p, which is sum of all the heads, total number of heads that I've obtained, which is going to be 2 over n. This seems logical, but what about 1, 1 and 1? In this case, I'm going to get a mu ml of 1. Okay, and what if I had obtained 0, 0 and 0? I'm going to get a mu ml of 0. So as you can see here, a minute variation could cause a greatly different estimation of my parameter. The reason why we have such a huge difference in our estimation is because the sample size is really small. So as you can see, by chance if I obtain 0 in the first toss, then my mu ml estimate for the second toss is going to be 0. Similarly, if I obtain the head in the first toss, then my mu ml estimation for the second toss is going to be 1. So what we can see from here is maximum likelihood estimation may not actually give you the right values of mu if you do not have enough samples. So now that we have seen what MLE is and one case in which MLE does not work, I just like to tell you in general when MLE would be the best to use. So MLE is an estimation technique that works best when you have large number of data samples with you. And you know the probability distribution from which the data samples were sampled distribution well. So this is a very critical point. So we have actually overlooked this point in the explanation that I did. So what I mean by this second point is that, so I assumed that I obtained all the data points from a Bernoulli distribution in the first case and from a Gaussian distribution in the second case. But what if I had actually obtained my x's from some other distribution in the second case but assumed wrongly that it was a Gaussian distribution? So you would actually see that MLE might not work really well if you make a faulty judgment about the distribution from which you have sampled. So this is something that you have to be really careful about, and you also have to be careful that you have enough samples with which you can do the MLE estimation. And just remember that when I say that you know the probability distribution well, you should know the parametric form of the probability distribution. That's all we have for the maximum likelihood estimation. I hope you have enjoyed this particular session. If you want to look at more interesting lectures, please visit www.projectria.org.